One of the most important applications of exponential functions is when we're dealing with compound interest. Now, compound interest is what happens when you put money into a bank account or some kind of investment, and they give you interest for it. For example, they might give you 12% interest on your money, and then they add that interest to your account. So, for example, if you have $30 invested in an account, they calculate 12% of that, then add that to your account at the end of the year, and then the next year you've got more in your account, you've now got a little bit more than $30, they have to give you a little bit more interest. They have to do 12% of the new amount that's in your account. Now, if you did $30 plus 12% of 30, that's like doing this piece of work in here. You would do 30 plus 12 over 100 times 30, or you could write that as 0.12 times 30. 0.12 is just 12% as a decimal. Now, another way of thinking about this expression then would be to say, okay, that's 30 times 1 gives you this, and 30 times 0.12 gives me this. So it's like 30 times 1 plus 0.12, or it's like 30 times 1.12. So if you want to know how much will be in your account after the first year, you could just do 30 times 1.12 if the interest is at 12%. Now, what's more, if you want to know what's in your account after the second year, okay, you can calculate how much is in there after the first year by multiplying by 1.12. To go from this number, the amount after the first year, to the amount after the second year, you would just have to multiply this number by 1.12. Or you could take the original amount, 30, and multiply it by 1.12, and then by 1.12 again, or by 1.12 squared, to get this new amount. If you wanted the amount after 4 years, you could just do 30, and instead of doing times 1.12 times 1.12 times 1.12 times 1.12, just multiply by 1.12 to the power of 4 to get straight to your answer. Now, that is what we do if we have a 12% interest rate. If we have 30% interest rate, we'd have to multiply by 1.30. If it were 93%, we'd have to multiply by 1.93. 3%, we'd multiply by 1.03. Now, 0.5% is like 0.5%. We would have to multiply by 1.05, but 1.005. Now, you'll notice while we're doing all that it's always useful when we have this kind of thing to re-express the percentage as a decimal. So think of the 30% as just being 0.3. Now, if you've got a positive R, that represents an investment that's going up in value, that's increasing. If your R is less than 0, then that represents something that's decreasing in value. So if you wanted to talk about a car, every time you buy a car, that's every year it goes down in value, perhaps by 25% per year, that's like going down by 25%, so you have to think of the R as being negative 0.25. Right, we have to multiply by 0.75 every time. Now, if you want that all in terms of a formula, this is a formula here that you can use. The amount is the amount after a certain number of years. In fact, after T years. The P is called the principal. It's the original amount that's in your account, that's put in your account. And the R is the percentage, is the annual interest rate, but expressed as a decimal. Okay, so T is the number of years, R's the interest rate as a decimal, P is the original amount invested, the principal, and A is the amount at any time. So if you're trying to answer this question here, and where someone's put in 250 euros in a bank and gets 15% compound interest annually every year, how much will be there after 10 years? Well, what you've got to do is take that 250 and multiply it by 1.15 to the power of 10. Can you see the similarity between this expression here and this expression up here? The P is 250. The 1 plus R is the 1 plus 0.15. We've converted 15% into 0.15 and we've added it to 1. And the 10 is a number of years. The second part of this question is to say approximately in how many years will it take the investor to double the investment? Not a particularly easy question to answer. After T years, the whole investment is going to be 250 times 1.15 to the power of T, whatever T is. So we've got to solve the equation that we have here. 250 times 1.15 to the power of T equals 500. Now, in a few weeks' time, when we look at logarithms, you'll see quicker ways of solving this. However, at the moment, what we've got to satisfy ourselves with is trial and error types of things. So what we do is we divide both sides by 250 to get this equation here. We then try various values of T. If you try T equals 3, that's too small. T equals 4 is also a little bit small. It's not quite giving us 2. When we try T equals 5, it's giving us a number that's slightly more than 2. So we can say that it'll take sort of between 4 and 5 years. In fact, it will take until the end of the 5th year before it's more than doubled, if you like, until it's actually doubled. Now, if you had an investment that was 500 Swiss francs, and let's say there's 12% annual interest rate, but the interest was compounded monthly, so it's put in every month, we'd have to do the calculations in a slightly different way. Okay, we know that it's 12% per year. What we would do is we'd translate that so that it was just 1% per month. And we'd think about the 3 years as being 36 months. We'd be adding interest 36 times. In other words, we'd have to be multiplying by 1.01, we'd have to multiply by that 36 times. So our equation would be 500 times 1.01 to the power of 36. Notice that gives you a value that's slightly more than the value that we got before. So generally, there's a kind of more general formula for that. If we've got compounded periods that aren't just years, we divide the interest rate by however many times we have to add interest per year. In our example here, it was by 12 because we compounded monthly. And then this number up here has to be the number of years times the number of compounding periods, the number of months in our case. If it asked us to compound, instead of compounding at the end of each month, we had to compound at the end of each day, we'd have to divide the interest rate by 365, because there are 365 days in a year, and then do the number of years times 365 up here. So in this question, example 3, we're asked to put 2,000 Swiss francs into an account at an interest rate of 5% for 10 years. First of all, by compounding annually, so we add interest only at the end of each year, and here compounding quarterly. There are 4 quarters in a year, so it's every 3 months we add interest, every quarter of a year. So in this example we would have to use the original equation, the first equation in here. We just do 2000 times 1.05 to the power of 10, calculate that, and we'll get 3,257 francs and 79 centimes. So that's straightforward. However, in the second example, we would have to enter this. Now, notice what's happened. The 0.05 is the interest rate as a decimal. We have to divide it by 4 because there are 4 quarters in a year. And instead of having just 10 years, we would have 40 quarters in those 10 years. 10 times 4. If you calculate that, what we should get in the end, once we've made things a little bit simpler for ourselves, is 3,287 francs 24 centimes. Again, slightly more than this value here because I suppose we're adding interest earlier when we compound quarterly. And the last example, example 4, is asking what annual rate of interest would be necessary. Right, so we're looking for our R in this case, for a principal of $100 to grow to $150 in 3 years' time if the interest were compounded monthly. So we have to use this equation here. Now your A in this example here is the amount that it's going to grow to. It's going to grow to $150. The P is a principal. The original amount that we put in is 100. The N is the number of times that we add interest in a year. If it's compounded monthly, then that means that the N is equal to 12. And the T is the number of years, and in this example it's 3. So setting up an equation, right, just plugging in those values, should give us something that looks like this. Right, we can then simplify that a little bit. If we do that, we should get something that looks like this. Now that's not an easy equation to solve, and in fact later on we'll possibly find easier ways of solving this. However, it's something that we should be able to do. Right? We take the 36th root of 1.5, or think of it as being 1.5 to the power of 1 over 36. If you do that, we should get this as our equation. When you're doing these types of equations, keep this to as many decimal places as possible. Don't round very much. Keep 5 or 6 decimal places if you possibly can. Then we'll have to take the 1 over to the other side. So we get this. And then finally, we'll just have to multiply both sides by 12 to get R. Now, this is R as a decimal. This is your interest rate as a decimal. So what we would need to do, we'd need to have an annual interest rate of about 13.6%, because this decimal here, when you convert it into a percentage rate, would be 13.6. Just move the point 2 places. 13.59, 13.6.